Hello again. Now, I'm going to go through with you this video from DNA Learning Center, and I want you to listen up. And I'll try to explain as we go through. All right.
During DNA replication, both strands of the double helix act as templates for the formation of new DNA molecules.
Okay, I've just paused the video. So here you can see the original strand, and then this is the helicase molecule that opens up the DNA. So it travels at about 10,000 revolutions per minute. And then here you can see, I mentioned that you have the synthesis of the lagging strand and the leading strand. So this is the leading strand, right? This is leading because this is the replication fork. This is the polymerase, and as this is available, so it just goes along synthesizing DNA along with the replication fork. Now this, on the other hand, is the synthesis of the lagging strand. You'll see later that there's a loop. This is the loop, and then synthesis actually goes that way, and then after it finishes, it will let go of that and then starts new synthesis to cover that region. All right, try if you can and see if you can recognize some of the molecules here. All right, so I've already mentioned that's the polymerase. I've also mentioned that that's the helicase, and you'll see if you can recognize other molecules.
Copying occurs at a localized region called the replication fork, which is a Y-shaped structure where new DNA strands are synthesized by a multi-enzyme complex. Here, the DNA to be copied enters the complex from the left. One new strand is leaving at the top of frame, and the other new strand is leaving at the bottom. The first step in DNA replication is the separation of the two strands by an enzyme called helicase.
Okay, it says that separation is done by an enzyme called Helicase, so this is it.
This spins the incoming DNA to unravel it at 10,000 RPM in the case of bacterial systems. The separated strands are called 3' and 5', distinguished by the direction in which their component nucleotides join up. The 3' DNA strand, also known as the leading strand, is diverted to a DNA polymerase and is used as a continuous template for the synthesis of the first daughter DNA helix. The other half of the DNA double helix, known as the lagging strand, has the opposite.
Okay, I'll just rewind a bit here. I want you to see something. Okay.
The other half of the DNA double helix, known as the lagging strand.
Okay, you find that this is the helicase. So what is this green one? This green molecule is actually the primase, and it will synthesize a new set of primer molecule so that once this polymerase finishes, it will let go of that and then start a new synthesis of a new region. Have a look at that. All right. If you find that it's a bit difficult to follow this video, you just need to follow one strand at a time, and then just keep rewinding so that you can see what's happening.
Has the opposite 3' to 5' orientation, and consequently requires a more complicated copying mechanism.
Can you see that?
As it emerges from the helicase, the lagging strand is
all right. So this is when the synthesis of that Okazaki fragment is finished. It lets it go, and then the polymerase now is ready to synthesize the new region of the lagging strand.
Organized into sections called Okazaki fragments. These are then presented to a second DNA polymerase enzyme in the preferred 5' to 3' orientation. These sections are then effectively synthesized backwards.
You can see in this footage that this is one of the Okazaki fragment that's been synthesized, and then this is a new one synthesis. Then it will reach that Okazaki fragment. And then you can see here the primer is coming back in again, and then this part of the molecule will then start over and then synthesize that part.
When the copying is complete,
See, there's a
the
primer
finished
molecule.
section is released and the next loop is drawn back for replication. Intricate as this mechanism appears, numerous components have been deliberately left out to avoid complete confusion. The exposed strands of single DNA are covered by protective binding proteins, and in some systems, multiple Okazaki fragments may be present.
Okay, so I hope, I mean, it mentions at the end that there's a lot of components that has been left out, so that it's quite clear. So have a look through again, and how this replication works. And if you have any questions, you have to make sure you have to ask me. You have to make sure you have to make sure to ask me the question, because otherwise I wouldn't know what you don't know. Okay, if I don't know what you don't know, then I don't know. Bye.